Hi you all. I was thinking about our review of resistivity and resistance, and I wanted to make sure that you all had a sense of what were, at least what I imagine are the important dimensions of resistance. So you recall we had this conversation about the performance, structure, properties, and processing, and how that related to resistance. And so, hold on, let's see here. I'm going to set this on the side here. You recall that we were looking at the resistance of, I pulled all this from Wikipedia. Anyway, this diagram, so we have a current that is flowing in an object of some length L with a cross-sectional area A, and the model of resistance that's typically used is shown in this equation where the resistance, right here, equals the resistivity, which is the material parameter, times the length divided by the area. So in my view, this is actually a very important relationship. And again, the material parameter is here in this value, the resistivity. And you may see that resistivity is represented like this, where the resistivity, well, let me kind of move some things around here, where the resistivity is organized in this way, and you see the geometric factors here and then the resistance here. I actually don't like this way of organizing it because, well, to me this is just much more intuitive, where you say that you have a resistance and you know that it's related to the geometry of the object, and obviously if it gets longer, the current has a longer distance to flow through something, then the resistance is going to go up. If the area is smaller, the resistance will also go up because the area is down here. And it makes sense to me that the resistivity, the material parameter, is proportional to the resistance. So notice that this one right here, of course, is independent of geometry. And that is typical of a material parameter. It will be independent of the geometry, like the density. That's independent of the actual geometry. So, in my view, this relationship, I would memorize this, or at least be able to figure it out, reason out that the resistance is proportional to the resistivity, and, of course, the resistance will go up when it's longer, and it will go up when the area that you are trying to squeeze the current through actually drops. So I almost always, remember this form of the equation. Now, other parts that I think are important in that conversation was this right here, that the conductivity is just, again, another material parameter, is inverse to the resistivity. And I think that let's see, you also may have seen an equation that looks like this, where you've got the resistance, or the resistivity, as a function of temperature equals some rho naught at some T naught plus basically alpha delta T, and this gives you the resistivity as a function of temperature. This is for linear dependence and really only holds for metals in a limited range. There is an equation for semiconductors, and that was this relationship here that we saw, where you have that the conductivity is, here I'll try to make this larger, the conductivity equals the number of carriers times E is the charge per carrier, or Q sometimes, times the mobility per the carrier. In this case, we're talking about electrons. For a semiconductor that is not doped, you have what's called an intrinsic semiconductor. This is not doped, and we'll get more into this later in the quarter. Not doped. the number of electrons will equal the number of holes, or excuse me, concentration. I'm saying this wrong. This is the concentration, and this represents the number of carriers per volume. So, you know, in intrinsic semiconductor, this is something like 10 to the 11th electrons per centimeter cubed. And so it's by definition, the number of electrons will need to equal the number of holes, because you actually create free electrons and free holes by breaking a covalent bond. And in the process of breaking that bond, so let's say you have silicon and you have an electron in a covalent bond, when you actually break one of these free, you create both a free electron and a free hole. And so you end up getting that the conductivity is equal to the sum of the number of electrons times the mobility electron times the charge, plus the number of holes per volume times the mobility of the holes. So here we have a term for conductivity. Now the thing that didn't come up in class, but I think is somewhat interesting, is that the mobility, and we talked about this just the other day, is equal to the charge over the mass, the effective mass, times the scattering. This doesn't look right. Charge, something's wrong with this equation. Not the velocity. I think it's the drift velocity, not the charge. Anyway, I'm going to need to look into this equation, because this doesn't, in this moment, this equation doesn't look right to me. Okay, I'm back. I looked into it, and I am wrong. This is charge over the effective mass, and tau bar is the time. This is the average time between scattering events. And this mu is actually called the drift mobility of the carrier. So I guess the thing that I'm trying to point out here is that people were asking, you know, how is it that you have a high mobility in semiconductors that or insulators? It doesn't make sense. Well, actually, semiconductors and insulators are they have very open structures, and, you know, for example, let's say, you know, I don't know, diamond is just made of carbon, and the carbon only has 6 protons, versus thinking about, you know, nickel has, I don't know, 54, something like that, 54 charge carriers in its nucleus, and as an atom. And you've got this very dense lattice. This is face-centered cubic. This is carbon. Diamond is something called the diamond cubic structure, which actually has a very large crystal lattice and has spaces in the lattice. So this you have, you know, very high drift mobilities in diamond, and very tiny drift mobilities in nickel, because the collision, the average time between collisions is small in nickel, because it's always running into things or being diverted by the charge in the nucleus, whereas diamond, it actually has somewhat of a free and clear path. So anyway, I hope this is somewhat insightful and helpful.